In the previous module, we discussed transport through single quantum dots. We discussed the single electron charging phenomena, Coulomb blockade oscillations, transport in large quantum dots, Coulomb diamonds, transport in smaller quantum dots, single particle states, and all those properties. So in this module, we will discuss transport in double quantum dots or coupled quantum dots. And the charge stability diagram. Transport in low bias and high bias regimes. And in the next lecture, we will discuss the transport in small double quantum dots. So in this lecture, we will discuss transport in larger double quantum dots. Okay. All these quantum dots are actually realized by electrostatic gating, but the physics that we are discussing is applicable to any kind of quantum dots which are coupled. Okay, so here what you are seeing is a gated double quantum dot device, a scanning electron micrograph of a gated double quantum dot device, where all these bright electrodes here represent the surface gates, and when you apply voltages you will form two quantum dots and they are coupled. When I say coupled, what that means is they are tunnel coupled. So the device or the system that we are going to discuss in this lecture and the next lecture is two quantum dots. They are tunnel coupled, they are in series with an external circuit. So what that means is the electrons can tunnel from one quantum dot to the other and then go to the periods or the other direction. In any case, tunneling of electrons between two quantum dots is an important aspect for all these devices. There are also capacitively coupled quantum dots where the effect is only electrostatic, but that is not what we are going to deal in this lecture. This is a slightly different geometry where when you energize all these gates with negative voltages, you will get two small puddles of electrons, which represents the double quantum dot system. Compared to this geometry, this design is found to be more attractive when you want to go to really low electron number or smaller quantum dots. Here is a simple representation, energy level representation of a double quantum dot system where you have two quantum dots, and I also have drawn two electrodes here, Vg1 and Vg2. That could be these two electrodes in this design, or maybe these two electrodes in this design, but they can change the electrostatic potential of the individual dots. For example, the Vg1 will preferentially change the electrostatic potential of this dot, whereas this Vg2 will change the electrostatic potential of this dot, the dot number 2. So we have dot number 1, dot number 2, and that is the terminology that we are going to use. And these gates are generally called plunger gates. Generally in the literature, they are referred to as plunger plunger gates. Okay, and here this is circuit representation of a double quantum dot system. This is dot number 1, dot number 2. They are coupled through a tunnel junction that is usually represented by a parallel combination of a capacitor and a resistor. So the capacitor means you can electrostatically affect each dot. For example, the charge on one dot can electrostatically change the potential of the other dot. And the resistor represents that there is also a transport through that. It's not just a capacitor, it's more like a leaky capacitor. All the tunnel junctions are of that kind. And source, there's a drain here, and these are serially connected. And you also have the gates VG1 and VG2. Those are the plunger gates we just discussed. They are connected dot by capacitor. Here it is actually just a capacitor. There is no tunneling of electrons from the gate to the dot. Okay, and this is the similar gate for the other dot. And there is also an extra capacitor I have drawn here, these two here. So these two represents the cross capacitance of the gate 1 to the dot 2 and gate 2 to dot 1. So these are really small geometries, structures, falls under few hundreds of nanometer, and the latest design, the latest generation of quantum dots are even sub 100 nanometer, in the sub 100 nanometer range. So changing the voltage on one gate will change the electrostatic potential of that dot, but that also will affect the electrostatic potential of the other dot. That means there is a cross coupling from gate 1, the gate of one quantum dot to the next quantum dot. Okay, so that is also there. That is also present always. But most of the discussion we will not concentrate on that aspect. That's kind of, you can think that's kind of an artifact of this design. Okay, but that is always going to be there. And the experiment you always will take care by compensating that voltage or that potential by applying an extra or additional potential onto the some other gate. So those are fine experimental details which will not be a part of this discussion. Okay, so what we have is we have two quantum dots. They are connected through tunnel junction, and each of these quantum dots are actually connected to the source on one side and the other dot to drain on the other side. Okay, and there are capacitively coupled gates which will enable you to change the electrostatic potential of the dot. And there is also a cross coupling capacitance that also will have effect on how you get how you look at the data, how you visualize the charge stability diagram. Okay, that we will touch upon as we move on. Okay, all right. Now let's consider the charge transport property. Okay, so what we have is we have two quantum dots. This is dot number 1 and dot number 2. Okay, and you have energy levels, charging energy levels. In this discussion, I'm not concentrating on the single particle levels. Okay, what I have represented is the electrochemical potential of the dot with the different number of electrons. Those are not the single particle levels. Now, and the assumption is these two dots are in series. You have source, dot 1, dot 2, then drain. So, with n1 electrons on one dot and n2 electrons on the other dot. So, the transport requires a change in number of electrons in this dot. Remember, these two dots are going to show single electron charging phenomena. Secondly, we are discussing the transport in regime where the applied voltage is less than the charging energy. That means we are in the single electron charging regime. So you cannot put two electrons at a time in one dot. And if the other dot already has an extra electron, then you cannot add a second electron to it. So both dots need to be in the charging or discharging regime to have transport going through it. If transport on one dot is blocked, then the overall transport is blocked because it's a sequential process. What I'm trying to say is, if one of the dot is in the Coulomb blockade regime, the other dot, it doesn't matter what state the other dot is, the transport to the whole system is blocked. So when you consider all these things with n1 electrons on one dot and n2 electrons on the other dot, usually you will start with an n1 and n2 charge state. So the first digit represents the number of electrons on the dot 1 and the second represents the number of electrons on the dot 2. Okay. Then this is the sequence, the charge, how the charge state is going to change when the transport happens. What that means is you add one electron to this dot, n1 plus 1, assuming that that dot can actually take the extra charge, or that dot is in an energy state where n1 plus 1 and n1 are degenerate. Then the next process would be, because you're adding only one electron, so the next process would be take that electron from the dot 1 and put in dot 2. That is the charge state. That what that means its charge state is going to be n1 and n2 plus 1, because now the extra electron has gone to the dot 2. So you have n1 and 2, then n1 plus 1 n2, then this electron goes to the n2, that means n1 n2 plus 1, that is here. Then finally this electron n2 will tunnel into the drain, then go back to n1 n2. So this is a sequence. Okay, that is one aspect. So that is one way to get the transport through. There is another way, is you start with two extra electrons. Now the transport is actually blocked. We can start in this range. But now you can have this extra electron n2 plus 1 that is here going into the drain. Then the charge will be n1 plus 1 n2. Now n2 can accept an extra electron. So that can go from n1 plus 1 state. So this becomes n1 n2 plus 1. Then n1 plus 1 n2 plus 1 eventually when the electron from the source tunnel into the dot 1. So in this process you're starting with a situation where n1 can take an electron. In this process you are starting with a situation where n2 can donate an electron to the drain. Okay, both of these processes are possible. Both of these cycles can give current through the dot. The whole discussion is happening under the premise that both dots are in the single electron charging regime. Now, just for example, say you have starting with 1-1 configuration, that you have one electron in this dot and one electron in this dot, then this sequence will be 1-1, 2-1, 1-2, back to 1-1. And this sequence would be, you are starting from n1 plus 1 and 2 plus 1, that will be 2-2, 2-1, 1-2, 2-2. So in both of these states, for example, these charge states, that is 2-1, 1-2, 2-1, 1-2 is common. Okay, both of these charge cycles will go through these two sequences, 2-1, 1-2, 2-1, 1-2. Okay. Now, let's consider the first situation where the interdot capacitance and the cross capacitance, that means this capacitor and these two capacitance are negligible, or they are almost not there. So that means they cannot change electrostatically the potential of each dot. Okay. For example, Vg2 cannot change the electrostatic potential of N1, Vg1 cannot change the potential of N2, and N1 cannot change N2, or N2 cannot change N1. That means the extra charge sitting on dot N1 cannot induce a change in potential on N2, and vice versa. Okay, that's what it means. But transport is possible, tunneling is possible. So this is a situation which is not really it doesn't really exist in practice, but we need to understand in this special case to move further. Generally, whenever there is a tunneling, capacitance coupling is almost always there. Okay. that is not a real one. This situation is not really a real life situation. That's what I'm trying to say. Okay. So in this special case, when I'm saying cross capacitance and inter-node capacitance are not there, what that means is charging and discharging events of each node is not going to affect the other node. But whether when you vary the potential of N1, you will not do anything to N2. When you vary the potential of N1, you will have more and more electrons tunneling into it or tunneling out of it. But that, or tunneling into this side or accepting from this side, but that is going to happen, but it's not going to electrostatically change the potential on N2. That's what it means. So these level diagrams here and these level diagrams here are not coupled. They are independent. Okay, that's what it means. Whenever I see VG2, I'll change only this one, I will not change this one, and vice versa. In this special case, we are going to look at how the charge transport diagram, that is called stability diagram, is going to look like. So the stability diagram for a double quantum dot is slightly different from a single quantum dot, because now we have three voltages to worry about. You have source drain voltage, that is source drain bias, you have gate voltage VG1, and you have gate voltage VG2. So what generally is done is you keep the source drain voltage constant, you don't vary that. Okay, you keep it a small value. Let's discuss the case when the source drain voltage is very close to zero. That means it is really, really small. Okay. Then we look at how the transport is going to happen when VG1 and VG2 are varied. So generally, stability diagram or charge stability diagram for a double quantum dot always deals with two voltages, the voltages on these two gates. It doesn't talk about the voltage on the source and drain, across the source and drain. That is always assumed to be small in the low bias regime, or it will be specified certain microvolts or millivolt, whatever that will be specified. Okay, but that is not really a variable in this case. The charge stability diagram discusses the space of VG1 and VG2 and what are the locations you are going to get transport. So in this special case, when you don't have any capacitance coupling, in this special case, when you vary VG1, you will make dot 1, you will vary only the dot 1 energy, and that actually can take electrons or donate electrons. And when you vary VG2, you will affect only dot 2, and dot 1 is left independent. It's not going to affect any parameters of dot 2. Okay. In this situation, to get transport through the system, you need to have both dots basically ready to accept electrons or donate electrons in a sequential manner. These are places where the energy degeneracy of each dot crosses. That means when the energy level of each dot is such a way that it actually can fluctuate the number. That is, N1 can be N1 plus 2, and N2 can be N2 plus, N1 can be N1 plus 1, and N2 can be N2 plus 1 or minus 1, or here also minus 1. These energy levels should be happen at the same point. That means VG1 and VG2, whenever VG1 enables the fluctuation of electron number on dot 1, and the VG2 enables the fluctuation of electron number on dot 2, these 2 points need to cross. What that means is, for VG1, when you vary that voltage, you will have various points where you can get the Coulomb blockade peaks. And when you vary VG2, you can also get a series of Coulomb blockade peaks, but these two need to coincide. So those are represented by wherever these two lines cross. Okay, and that is going to be that whole space of points where these two can fluctuate at the same time is going to look like a square or a rectangular lattice depending upon the symmetry of the system. Okay. So in this case, I have assumed they are symmetric. So you are going to get a square lattice. A point, these 2 points will be represented by a square lattice in VG1, VG2 space. So let's consider one specific point here, which is what we discussed here. That is, you can start from a situation where you have N1 and N2. Then you need to go through this sequence that N1, N1 plus 1, that is in this region, then N1, N2 plus 1, then back to N1, N2. That's what it is. So you are going through this cycle. So these 3 charge configuration, 1, 1, 2, 1, 1, 2, back to 1, 1. And this specific case, you are starting from here and you are going 2, 1, 1, 2, and back to 2, 2. So you can see that in this specific case, 1, 2, and 2, 1 charge states, and the voltage at which these two charge state overlap is one particular voltage, VG1 and VG2. Okay. So this is the situation when you have Cm, that is the capacitance between the dot, and these two cross capacitance are 0. When these two are 0, what you are going to have is a square lattice or a rectangular lattice of points wherever you are going to get currents through it. So these points represents in a IV characterization, in a current voltage characterization, the points on the gate voltage space, VG1 and VG2 space, where you are going to get non-zero current. So if you take a measurement with VG1 and VG2 varying and apply with a small bias, in this specific situation, the points or the gate voltages at which you will get non-zero current will look like a rectangular or square array or lattice. That's what I want to say. Okay. Now let us go to the next situation where these capacitances, the cross capacitances, are not 0. We are still considering Cm is 0. The interdot capacitance is 0, but the cross gate capacitance is not 0, but they are small. What that means is varying the voltage on one of the dot gate is going to affect the other dot also. So if you apply negative voltage on VG2, this will push these levels up, but that is going to push these levels on this also slightly up, because that capacitance is negligible, not negligible, but it is not 0. So there will be some rise in the levels of this dot also. That means the charge degeneracy point for this dot also will get affected by varying the gates on this dot. Okay. So what that means is the charge degeneracy point of this dot also will get shifted when you vary this gate, and vice versa. So again, the charge cycle is same, N1, N2, N1 plus 1, N2, N1, N2 plus 1, N1, N2 for this, and N1 plus 1, N2 plus 1, N1 plus 1, N2, then N1, N2 plus 1, and N1 plus 1, N2 plus 1. That is still a cycle. But what happens is, because of the cross coupling, the perfectly square or rectangular looking stability diagram is going to get slightly tilted now. And this is the way to look at that. Previously, these lines were straight. Okay. Those lines represent the charge degeneracy points. But because the charge degeneracy point is going to get affected by varying the other gate, you need to compensate whatever the variation onto its respective gate to bring back the charge degeneracy point or maintain the charge degeneracy point. So what that means is, when you this perfectly perpendicular or parallel looking, horizontal or vertical looking, this charge degeneracy array of charge degeneracy points is going to get slightly tilted, because now the charge degeneracy point of dot 1 is affected by the variation dot gate of the dot 2, and dot 2 by the variation gate on dot 1. So in this diagram, when you vary Vg1, okay, now 1 and 0, this is the charge degeneracy point for this one, and this is charge degeneracy line for 1, 0 and 2, 0. That means you are varying only the electron number of one of the dot. But that point, though all those things used to happen perfectly horizontal line, now got slightly shifted towards lower negative voltage, because varying Vg1 positive is going to affect where the charge degeneracy point of dot 2, so Vg2. So you can see that whenever you take Vg1 positive, you have to take Vg2 negative. That line is going to go slightly lower to compensate or keep that point, charge degeneracy point, same. And similarly, whenever the Vg2 is positive, you can see this line is going to go more into the positive side, then this line is going to go more on negative side. Okay, when this line goes to positive side, this line basically goes to negative side. Okay, what that means is, this cross capacitor is going to tilt the overall stability diagram, both charging lines for both dots, okay, so that the shift because of voltage is compensated. Okay, so that is the effect when you have the cross capacitance enabled. Now let's look at the real situation where you have both interdot capacitance and the gate capacitance and cross gate capacitance are non-zero. That means all these capacitance are shown in this diagram is there. So previously I had this situation where the charging lines for dot 1, dot 2 are actually not perpendicular, but they are tilted. That is this situation. Now you also have Cm, that is the interdot capacitance, also non-zero. So the effect of that would be the N1, N2 and N1 plus N2 plus 1, they cannot now lie in the same gate voltage. Previously, the 2-2 configuration and 1-1 configurations are degenerate at this point. At this point, you can have 2-2 or 1-1. That means the extra electron on dot 1 and dot 2 is not going to affect the potential. That and 1-1 electron and 2-2 electron happens at the same gate voltage. That is because the extra electron on dot 1 is not affecting dot 2. The extra electron on dot 2 is not affecting the potential of dot 1. But now that is not the case. When you have the capacitance, the extra electron on dot 2 is going to put a more negative charge or a lower potential on dot 1. Okay, what that means is 1-1 and 2-2 configurations cannot be degenerate. They can never be at the same point. That they will be shifted. They will be pushed. That means 2-2 can happen only at a slightly positive gate voltage compared to 1, 1, because that has an overall negative charge. That means you need, that charge configuration can be pulled to the transport regime only by the application of more gate voltage, or making the gate voltage more positive. What that means is, in the 1, 1, 2, 2 will be displaced such a way that 2, 2 will be slightly on the positive side and 1, 1 will be slightly on the negative side. Previously they were like this, now they will be shifted, and that is what we are seeing here. So you had this one originally, and that will be now shifted. Then of course the charge transport cycle is not going to get affected anyway, because that is still going to happen the same sequence. So then previously the diamond shape looking, so you started with the square or rectangular array of these non-zero current points in the VG1, VG2 space. Now that, and after enabling the cross gate capacitance, those start looking like a diamond shape. Okay, and that is what we had here. Now this one, by the introduction of the interdot capacitance, each of these points now split into two, and it's going to look like a honeycomb diagram now. So each of these points, previously was 1 point, right? Now they split into two, and now the charge stability diagram is going to look like a honeycomb structure, something similar to this, something as shown here. And this is how you label the charge configuration. So VG1, VG2 will look like a honeycomb, and that is the realistic picture. That's how a tunnel coupled quantum stability diagram should look like. Okay. So we started with no capacitive coupling, then enabled the cross-gate capacitive coupling, then these lines got tilted. Now enabling the interdot capacitance, you got these 2 points split, 2, 2, 1, 1, 1. Okay. Now these 2 cycles, that is N1 plus N1 and 2, N1 plus 1 and 2, N1, N2 plus 1, N1 and 2, and N1 plus 1 and 2 plus 1, N1 plus 1 and 2, N1 and 2 plus 1, N1 plus 1 and 2 plus 1. These 2 cycles now will happen at different gate voltages, 2 different gate voltage, set of gate voltage. Previously, they both can happen at the same gate voltage, but that's not a realistic situation. Now, this happens at a slightly positive gate voltage, but this happens at a slightly negative gate voltage. So, these 2 gate voltages and these 2 gate voltages. Okay. That means these 2 points now got separated. So in summary, what we have is, to have transport happening through the system, you need 3 charge states, that is N1, N2, N1 plus 1, N2, N1, N2 plus 1, and N1, N2 degenerate. And similarly, another case, starting from N1 plus 1, N2 plus 1. If you look carefully, this is two of those edges, 2 of those motifs of the honeycomb. In this case, this is like an electron going in one direction. If you check the other one, you start with an electron tunneling out of system to drain. That is equal to a hole tunneling into the system. So if you look at this one, you start from here, electron tunneling out, then electron tunneling into this dot from the dot 1, then finally the electron tunneling from the source to dot 1. This is like a hole going backwards. This is the electron going forward. This is like hole going backward. That is how the charge cycle happens. First of all, these 2 points, you need to have 3 charge states in equilibrium. That's why these are generally called triple points. They are charged triple points, so 3 charge states are degenerate. Secondly, the way the charges flow through system, they vary through system. Looks like electron going through the system the forward direction for the lower triple point, whereas the hole going into the reverse direction that will drain to source. That is in both cases. Let's be clear here. In both cases, transport always happens by the motion of electrons. This is an electron quantum dot. It's not a hole quantum dot. What I'm discussing. You can also have hole quantum dot. Okay. But in this case, the way you can visualize this one is like an electron going in the reverse direction. Okay. And when you have none of this coupling enabled, what that means is none of this capacity coupling like interdot capacitance or cross-gate capacitance enabled, you have only two directions. You had only two vertical, the vertical direction and the horizontal direction, right? Because all these points were arranged like a square or a rectangular lattice. In the VG1, VG2 axis. But now you have a honeycomb structure. So here you had only two directions, this horizontal direction and this vertical direction. But now, after the introduction of these capacitances, you have three directions. If you look carefully, you have a direction this way, and you have another direction this way, and you have three directions in the system. Okay. And these three directions, you need to go through these three directions, you need to vary the voltage on both gates. Okay. For example, if you go through this direction, this red line, you will vary only the potential of the dot 2. So now remember, previously you are going perfectly vertical for dot 2, because that is under assumptions that you are not changing anything regarding dot 1. Okay. Now, if you go straight vertically up, you will change the potential of dot 2, but you will also change the potential of dot 1. So to compensate that, you need to go in slightly at an angle in the stability diagram, so that you are not changing only voltages on the dot gate 2, but you are also changing the dot gate from voltage 1. So the upward direction in this angle is making the voltage on dot 2 positive, but making the voltage on the VG1 at dot 1 negative. That means whatever you are going to induce on dot 1 by dot 2 need to be compensated to keep that levels there. Keep that level steady. So if you go straight up on VG2, then you will vary both dot 1 and dot 2. So the degeneracy lines for individual dots are now tilted. That's what we discussed in the previous slide. So when you go through along the red line in this diagram, you will vary only the potential of dot 2. Similarly, when you go along the blue line, the dark blue line, you will vary only the potential of dot 1, but dot 2 will be kept invariant. Okay, so in this case, mu1 does not vary. Mu1 is the electrochemical potential of dot 1, but only mu2 vary. In this case, mu1 vary, but mu2 does not vary. Similarly, the third direction is the light blue line or teal line that is connecting the two triple points. Along that, you will vary both VG1 and VG2 by the same amount. Okay. What that means, you will lift both levels up or lower both levels down, depending upon which direction you are sweeping. So that direction, you will change the potential of both dots. Okay, so previously you had two direction as shown here. Now that has split into three directions. Okay, because you have now you have got a hexagonal or honeycomb stability diagram. Now this is just a summary of what we discussed so far regarding the stability diagram. You have three charge cycles, three so you have three charge states degenerate, two kinds of charge cycles. This is the electron and this is the whole triple point. Okay, they arrange into a honeycomb shaped structure in a in the VG1 VG2 space, and these two charge states are common for both. Okay, but they are not degenerate, they are shifted now, but those states are common because the voltages this happen for electron triple point and voltages at which it happens whole triple point are shifted slightly, that we discussed already. Okay, and this is the situation, this is how the charging diagram going to look like when you have the source drain bias very close to zero or almost zero. Okay, now just very quickly look at the equations or parameters that enter or that you can get from the stability diagram. So electrostatic energy of the whole system, whole dot, is given by this, where you have n1 electron on dot 1, so n1 square EC1 will be the charging energy or electrostatic energy of the dot when you have n1 electrons on dot 1. This is for dot 2, n2 square EC2, and this is how n1 and 2 EC1, ECM, the electrostatic energy of dot 1 is going to change when you have extra electron dot 2, and dot 2 is going to affect when you have an extra electron dot 1. Okay, and f of some function of Vg1 Vg2, and that is given here. This is all very simple, mathematics. You just need to rearrange terms, where this EC1 is given by E square by C1 to 1 plus 1 minus Cm square by C1 C2. Now remember, this EC1 charging energy is not just a function, it involves all the capacitances. It also involves Cm, the interdot capacitance too. The moment this capacitance goes to zero, that means it will be just the charging energy of that individual dot, only for that dot. Similarly, EC2 also has the coupling capacitance, Cm. And ECM is the effect of having charging happening on another dot on the next dot. So that is given by this term. So when you have the interdot capacitance ECM0, the whole electrostatic energy will reduce to the sum of two electrostatic energies of two dots. This is the electrostatic energy of dot 1. This is the electrostatic energy of dot 2. So when you have the Cm, the interdot capacitance 0, this will be for the dot 1, and this will be for dot 2. That's it, because there is no effect of charging of one dot on the other. And from the honeycomb stability diagram as shown here, you can extract various parameters like delta Vg1 and delta Vg2 are the periodicity in the horizontal and vertical direction. From that, you can get the gate capacitance, because those are the Coulomb blockade oscillations for that respective dot. So if you vary only Vg1, you are getting a series of peaks. That is the Coulomb blockade oscillation of that particular dot. From that, you can get that capacitance, Cg1 and Cg2. And similarly, from delta Vg1m and Vg2m, you can get the interdot capacitance. Okay, and just by looking at the charge stability diagram, you can extract various, in summary, you can extract various um, device, various parameters connected to the device geometry. So until you have a charge stability diagram which looks like a honeycomb, you cannot tell that you have a tunnel coupled double contour system. So this is the touchstone signature or phenomena, or this is the signature that you need to show. So you need to look in the transport of a double contour system. Without this, it is not clear whether you have a double contour system or not. So this is probably the first and maybe probably the most fundamental measurement that one would be doing using a double contour system. All right.